In the previous chapter, we talked about properties of materials and discussed if we want to achieve a desired property, any kind of property from mechanical to optical, electrical to magnetic, we need to understand and thus modify the structure. And we learned that structure controls the properties, and we have given examples to this basic concept. So basically we understood how important the structure is. And by atomic structure, of course, in this chapter we're going to cover atomic structure and bonding. And by atomic structure we mean basically the electronic structure of atoms and the binding forces in between the atoms. And later it is gonna be 3D arrangement of atoms throughout the materials. So that is what atomic structure covers. And of course, arrangement of atoms, this is very important concept, because even if you have identical composition, meaning you have the same atom, and different atomic arrangements can result in different properties. And we have given example of steel last time that was cooled down at different rates, and it ended up having different atomic arrangements and thus different strength. Another great example to this is graphite and diamond. Both are made up of carbon atoms, but in diamond, carbon atoms are arranged tetrahedrally. So it's like a 3D network structure. For this reason, diamond shows extraordinary strength and hardness. Diamond is the hardest material known. It will scratch all other materials. It is also the best heat conductor and conduct 5 times of that copper does. And all because of these atomic arrangements, graphite and diamond shows different properties. So on the other hand, the carbon atoms in the graphite, they are arranged in layers, and those layers are attached with weak forces. Therefore, it is soft and has lower density than diamond, basically. So in this chapter, we're going to address the following issues. What characteristics of atoms or molecules promote interatomic, intermolecular bonding? So interatomic bonding means bonding in between atoms, and intermolecular means bonding in between molecules. So we will basically learn why certain atoms experience certain types of bonding. Then we will learn what types of interatomic, intermolecular bonds exist, and what properties depend on the magnitude of interatomic, intermolecular bonds. So bonding strength, of course, will control many of the properties we're going to see, such as the stiffness of the material, meaning how it is easy to deform it, or thermal expansion coefficient, or melting point. These type of properties will directly related to the bonding strength. Okay, and let's start with looking at the structure of the atom first and learn about the electronic structure, because it is very important to understand the electronic structure, because it directly controls the bonding of atoms together. An atom is built with a combination of 3 distinct particles: electrons, protons, and neutrons. Each atom has a center nucleus where protons and neutrons are densely packed together. And of course, surrounding the nucleus, we have a group of electrons orbiting, right? And we know protons are positively charged, electrons are negatively charged, and masses for these particles, they are extremely small and given in this slide. Like electrons are 9.11 times 10 to the power of minus 31 kilogram, Protons and neutrons, they have a similar mass, 1.67 times 10 to the power of minus 27 kilogram. So the number of protons in an atom is important because it defines what chemical element the atom represents. For example, an atom with just one proton is hydrogen, and an atom with 29 protons, for example, is copper, or an atom with 94 protons is platinum. So the count of protons is called the atomic number, and you can see, and it is also equal to the number of electrons in neutral species. And atomic number is represented by the letter Z. And the atomic weight of an atom is equal to the sum of its protons and neutrons. The atomic weight of an atom or a molecule may be specified on the basis of atomic mass unit per atom or mass per mole of material. So two different ways to specify atomic weight. So by definition, one atomic mass unit, or abbreviation AMU, okay, atomic mass unit. So by definition, one atomic mass unit is equal to 1 over 12 times of the atomic mass of the most common isotope of carbon, carbon 12. So basically, 12 times 1 over 12 gives us one atomic mass unit. So think about it like each atom is like one atomic mass unit. So as we said, atomic weight can also be expressed as the weight of 6.022 times 10 to the power of 23 molecules or atoms. So this is Avogadro's number. So there is the relationship in between them. So basically, one atomic mass unit per atom represents 1 gram per mole. Of course, we usually prefer to use gram per mole. So it is like representing the weight of Avogadro's number of molecules and atoms. So examples, carbon is 12.011. That means carbon is 12 atomic mass unit. Okay, this you can read it as carbon is 12 atomic mass unit. It has 6 protons and neutrons. Okay, so and we can also say 12 carbon is 12 gram per mole. You can also say that. Okay. So atomic structure, of course, controls all sorts of properties: chemical, electrical, thermal, optical. So now let's try to understand the motion of electrons in an atom. So when we are trying to explain motion of electrons, actually we need quantum mechanics. So classical mechanics assumes exact knowledge of position and motion of electrons. So remember, in simple models, like if this is the nucleus, around the nucleus we are drawing like this, there is an energy level, and then we are putting electron right here, like as if we know it. But in reality, it is uncertain, because for very small particles like electrons, there is always uncertainty involved in defining the position or the motion of electrons. So this is actually the Heisenberg uncertainty principle. This is the fundamental theory in quantum mechanics that tells us one cannot determine the precise position and momentum of electrons at the same time. So we won't go into details, of course, but if you guys are interested, I provide you guys link in Canvas. You can watch the videos. I will try to simply explain why such uncertainty exists in terms of defining where the electron is, okay? So for example, you are trying to measure, let's say, the velocity of electrons. Of course, how are you going to do that? You will need to send some photons so that it will interact with the electron, and somehow it will come back to your eyes and you will be able to say, oh, there is the electron. But once actually you send the photon, right, it is no longer the case. It is no longer there, because as you observe the electron, your photon has caused it to scatter in all directions. So it can go anywhere actually. So we don't even know which direction the photon came from. So there is some uncertainty involved regarding the momentum and the position of an electron. But what we can do, we can say electron can be in this specific region, in certain specific region, because we can make a guess. There's a probability that it will be on that region, right? So therefore, to overcome this problem, the uncertainty problem, it is necessary to explain the position of an electron using probability. So we cannot actually give the exact position or velocity of an electron, but we can give finite probability of finding the electron over a considerable distance. The main understanding and important lesson here, you guys need to understand that don't think electrons as single particles. Although we tend to draw them like that, right? Although we tend to draw them like single particles, think about them as a cloud of probability density. So it's like a cloud. Within that cloud of probability density, electrons can be anywhere. So actually, scientists figured out that electrons are actually waves, and many of the mathematical equations prove that. One of them is Schrödinger equation. Again, you can watch the video related to that if you're interested. But Schrödinger equation was an equation that was able to be solved only when we assume wave-like properties of electrons. And it was also found that to be able to solve this equation, there are only specific values of energy for which there is a solution for the equation. Okay, so there is not a continuous range of energy states available to the electron, but discrete set of energy states available. And that is also what is called quantized. So many times we come across with this word in quantum mechanics, the term quantized. That means we have discrete set of possible energy states. That means we already know this, like energy level 1, energy level 2, energy level 3, like discrete set. It is not going to be 1.5, energy level 2.5. It will always be 1, 2, 3. This actually proves the wave-like properties, but we won't go into details, and I'm sure there were explanations in the videos that I send you guys. Okay. And so we understand that the exact position is described by a probability function, like an electron cloud. And in wave mechanics, in quantum mechanics, basically every electron in an atom is described by 4 parameters called quantum numbers. Okay, the size, shape, and the orientation in space of an electron probability density are specified by quantum numbers. Think about quantum numbers describing the precise location of electrons. Think about them as a home address. So each electron is described by a quantum number, meaning its address around the nucleus. Like a quantum number is its street address, one quantum number is zip code. But each electron will have a unique set of quantum numbers that is describing its location around the nucleus. Okay, so those are going to be the quantum numbers here we learn. So this way we can describe the position of the electron around the nucleus. So the first one is n. N is the principal quantum number. It describes the energy level. We also call them shells. Okay, so that means it takes only integer values, energy levels 1, 2, 3, and sometimes it is called K shell, L shell, M. Like these are around the nucleus. And L is the subshell. It is angular momentum quantum number, and it gives information about the shape of the orbital. What it is, for example, S orbital, like it is a sphere, S orbital. So that is, think about this cloud. Within this cloud, electrons can be anywhere. So within this sphere, S orbital, electrons can be located anywhere, like a probability distribution or electron cloud. Okay. So ML is the magnetic quantum number. This specifies the orientation in space, X, Y, Z directions. And finally, spin quantum number. Electrons do not only orbit around nucleus, but they also spin around their own axis. And each orbital can have maximum 2 electrons. So spin quantum number can have 2 possible values here, plus 1/2 minus 1/2, meaning 2 electrons spinning in opposite directions. So we have learned electrons have discrete energy levels. We can now look at the complete energy level diagram for various shells and subshells. So for energy level 1, 1s, 1 here represents the n, the energy level shell. S is going to be the subshell and quantum number L, right? Thus it tells us that we are located at the first energy level, closer to the nucleus and closest to the nucleus, first energy level, and the orbital is S-shaped, and within this S-shaped orbital there will be 2 electrons in this subshell and spinning, of course, in opposite directions. So you guys need to keep in mind, smaller the principal quantum number n, meaning the lower the energy level, it is closer to the nucleus. So that means energy of 1s is less than 2s. So to understand the total electronic structure of an atom, we need to know how many electrons we need for each state and which of the quantum states are occupied. So each set of quantum numbers, as I told you guys, specifies a particular energy state, quantum state of an electron, for an electron. Question is then, which of the quantum states are occupied? And Pauli exclusion principle tells us no 2 electrons in a given atom can have the same set of quantum numbers, meaning each electron will have a unique set of quantum numbers. Okay, so electrons, right, will always occupy to those quantum states of lowest energy first, and which are closer to the nucleus, and they are more stable therefore. So starting from the lowest energy level and levels, electrons will continue fill up till the highest energy levels. The electron configuration represents the manner in which these states are occupied. The number of electrons in each subshell is indicated by the superscript after the shell-subshell designation. For example, the configuration, the electron configuration 1 for hydrogen is 1s1, right? And this means we are at the first energy state. S is the subshell, which is in the shape of a sphere. It has 1 electron in it. Okay. So in this slide, you guys can see the electron configurations for some common elements. So for an atom to be stable, meaning not willing to participate in a reaction or bonding, the outer shell must be completely filled, and usually these are noble gases like helium, neon, argon, krypton, right? The outermost shell, the valence shell, is completely filled in these atoms, but the rest, it is not filled, so they are not stable, meaning they can participate in reactions or take part in bonding. So basically, therefore, valence electrons, these are the electrons that occupy the outermost shell, outermost basic energy level. And these electrons, very important because they participate in bonding between atoms. And some elements, as we have talked, have stable electron configuration, like noble gases. And that means their outermost shell is completely filled with electrons, and those were noble elements such as neon, argon. They are inert and unreactive chemically. And some atoms have unfilled valence shells and want to gain or lose electrons and achieve that stable configuration, noble gas configuration. And this is basically the basis for atomic bonding. An example to electron configuration is given in this slide, iron, and atomic number is 26. So electron configuration, as you can see here, if we write down the electron configuration starting from the lowest energy level, first energy level will be occupied with 2 electrons, as you can see, spinning in opposite directions. And the second energy level, we are seeing it has 2 subshells, S and P. We need to understand that the second energy level also has a p orbital, and p orbital actually has 3 different alignment in space. It means it can align in x, y, and z directions, and each of these will be occupied with 2 electrons. If I try to draw the p orbital, p subshell, it is gonna be, so if it's a z-axis, y-axis, and x-axis, right? Remember, the orientation in space is also described by a quantum number, right? M. And so s orbital was a sphere, and p orbital is gonna look like this, okay? And it can align on XYZ directions. So it is like a probability cloud within this cloud, electron can be anywhere, okay? Of course, only two electrons can be found in one orbital. Let me delete this. Okay, and then of course p orbital can also align in the z direction and x direction. So think about this is the electron cloud shape. Within this cloud, electrons can be anywhere. Okay, so as we can see, then we have 4s coming and then 3d. So in some cases 4s, because 4 is a higher number than 3 energy level, right? But in some cases 4s can have a lower energy than 3d, because think about it, these are electron clouds, spaces, distributions in space, so they can be very close to each other, they can also overlap. So therefore, in some cases, 4s can have a lower energy than 3d. And electrons will fill these orbitals in a way to achieve the lowest energy configuration possible. And in this case, 4s will fill up first, and 3d orbital will accommodate the remaining 6 electrons. When we look at periodic table, it has 118 elements, and elements are arranged, of course, based on their electronic structure. Within each square is the symbol of atom, as we can see, and its atomic number and atomic mass. Atomic number, we know, is the number of protons in the nucleus of an atom, and from left to right and top to bottom is an increasing atomic number. The horizontal lines are called periods or rows, and we have 7 rows, right? These 7 rows also corresponds to the principal quantum number and energy level. Okay, vertical lines are columns or groups, and we have 18 groups. They are the number of electrons in the outermost energy levels, basically. And also elements in the same groups, right? This one. Elements in the same groups, they have a similar chemical properties, since basically the valence electrons are the same. The number of electrons in the outermost energy levels are the same. Group 1 here, their alkali metals have 1 valence electrons and they are highly reactive. Group 2, alkali earth metals, they have 2 valence electrons. Group 17, for example, are halogens, and they have 7 valence electrons and would love to get an electron. Right next to it is unreactive noble gases here. And these are used in applications to prevent chemical reactions, such as argon, for example, used in light bulbs to prevent the tungsten filament from oxidizing. In between, of course, there are transition metals. And let's look at some trends here. Atomic radius will increase when we go from right to left, and top to bottom. When we are moving within the same shell, meaning the same quantum number, right, the same row, as the number of protons increase, because it will attract electrons more strongly, it will decrease the atomic radius. And ionization energy, which is the energy required to move an electron from an atom, and when we are farther away, an electron from a nucleus easier to pull away. So ionization energy increases as we go from bottom to top and left to right. For example, francium here is the easiest, whereas the helium requires the most energy. And electronegativity is the same trend, has the same trend as the ionization energy. What is electronegativity? Electronegativity is the tendency of an atom to attract electrons towards itself. Electronegativity is therefore increases when we go from left to right and from bottom to top. So electronegativity is actually sometimes represented with a dimensionless quantity, and it ranges from 0.7 to 4, 0.7 being the francium here. And of course the larger values will mean the larger electronegativity. And we see fluorine is 4. Okay. Highest, from lowest to the highest. Okay. So electronegativity of an atom is basically, we learn, it's a measure of its affinity for electrons. And the atoms of various elements differ in their affinity for electrons. And so the relative electronegativity of two interacting atoms plays a major part in determining what kind of chemical bond will form between them. So if there is a large difference in electronegativity, just in this example we are given magnesium and oxygen. Oxygen atom is taking 2 electrons from magnesium. And of course, this converts magnesium into an ion, like magnesium 2 plus, when it loses its 2 electrons, to oxygen. And of course, oxygen receiving, forming also an ion, oxygen 2 minus. So this is what we call the ionization process. And basically the ionization process is creating ions, and they have opposite charge, so they are forming the basis of ionic bond formation. Okay, so one of them basically gives electrons to the other, forming the ions, because they have dissimilar electronegativities, and therefore this is resulting the formation of ionic bonding. Because ionic bonding is the result of electrostatic interaction between ions, metallic and non-metallic elements. In this example, we have sodium chloride and sodium chloride. Of course, sodium metallic elements easily give up their valence electrons to non-metallic element. In this process, they become ions, sodium ion and chlorine ion. Okay, and then there's gonna be an electrostatic, actually attractive bonding forces are Coulombic. Those forces are forming the ionic bonding. So to understand atomic bonding, we will study how two isolated atoms interact when they are brought close together from a finite separation. So here we are seeing the potential energy versus the separation distance between atoms curve. So when they are far away, separated from each other, right, like this. So there will be two forces at play, attractive forces and repulsive forces. Okay, attractive forces and repulsive forces. And of course, the magnitude of these forces will depend on the interatomic distance, R. Interatomic separation distance, right, R. Actually, this starts from the center of the atoms. Okay, so of course in ionic bonding, one is positively charged, one is negatively charged, right? So they will start to attract each other. But then when they are coming close together, the electron clouds surrounding these atoms, we both will be negatively charged electron clouds, right? They will be repulsive forces. So initially these ions, because one is positive, one is negative, they are attracting. So when they are far away from each other, but as they approach together, right, because of the electron clouds in between, in surrounding these atoms, both are negatively charged, will start to repel each other. So at large distances, of course, when the atoms are far away, right, far away, these interaction is very negligible. And only the attractive forces will be in play. Okay, will be in play. So we are also seeing, as you can see with the blue here, that is basically the attractive energy line there. Okay, like this. So first attractive forces are played, then they will start to come together due to these attractive forces, and the potential energy is decreasing as they approach each other. As you can see, as the atoms getting closer to each other, R is decreasing because they are getting close because of the attractive forces, and potential energy is decreasing. Initially they start with zero potential energy, and they are getting negative potential energy, meaning they are getting through a more stable configuration. But of course, as we said, they approach and the electron shells overlap, and a repulsive force will be in effect. And here the repulsive force are shown with the green. Okay, when they are coming close together, they will start to repel each other. Okay. When the attractive and repulsive forces are equal in magnitude but opposite direction, that means there is no force. And if there is no force, then we can say we have reached equilibrium state. So this is where we reached equilibrium is basically the centers of two atoms remain separated by the equilibrium spacing R naught. So we are at this point, we call this R naught, and we have reached the equilibrium separation distance. Okay, and that means the forces acting on the atoms, the sum of them is zero. And at this interatomic equilibrium spacing, the potential energy of the atom pair is minimum. Okay, as you can see, this red line, the red line is our curve, energy curve, is the sum up of the energy, repulsive energies and attractive energies, and the sum is giving us this curve here, the red one. Okay, so as you can see, when we reached the equilibrium separation distance, that is giving us actually this E naught energy. Okay, the potential energy E naught in the equilibrium is actually a measure of bonding energy, or the energy that is required to dissociate the atom pair, to separate ions. But the atoms will not be able to approach the closer than R naught because of the repulsive forces, right? Okay, the repulsive forces increases much more rapidly with decreasing separation than attractive forces. Okay, so their relationship with the changing R is different. Their dependence on the R is different. And you guys need to remember how the energy and force is related. From other classes, you might remember that energy is basically force times the distance, right? So if we talk about infinitesimal changes of energy, this is force times distance. So we change infinitesimal changes in the distance times the force is giving us the energy change. And the net energy is the sum up of attractive and repulsive energies, as I showed you guys in the graph. So it has been found that basically the attractive energy is related to the interatomic distance through this equation, minus A over R. And minus A over R, R is the separate distance, a separation distance, and A is a constant. Similar to that, as we said, with repulsive forces, repulsive force basically increase much more rapidly with decreasing separation compared to the attractive forces. So the relationship given for the repulsive energy is B over R to the power of N. So in this case, B and N, they are constants. So another important point here is that the ionic bonding is non-directional. That means the bonding strength is equal in all directions around the ions. So the ions come together in all directions. They don't have a preferred direction. We're going to later see that some bonding types, they have a preferred direction. So we call them directional bonding. But ionic bonding is not a directional bonding. It's non-directional. There are many things we can learn from such a energy diagram. Okay, so what we can learn is, we learn that binding energy of an atom is basically represented by the depth of this potential well. So we call this part, let me choose some color, this part is the well, potential well, and the depth of it is giving us, of course, at the equilibrium separation distance, right, at this point, the depth of it, okay, is giving us the bond energy. And the location of this minimum determines the equilibrium separation distance R naught, or the bond length. Okay, so this is representing us the bond length, this is representing the bond energy. So we can relate this to this information if we have this curve for different types of ions. What we can give information about is, for example, the bonding strength. right? Bonding strength. We can get information about elastic modulus. We're going to learn what that is, but it is related to the strength of the bonding. Thermal expansion coefficient, melting points, and usually basically bonding energy directly related to the melting point, how strong the bonding is. Of course, you need to give more energy, so it is going to increase. If it's a strong bonding, it will have a higher melting point, higher stiffness or elastic modulus, and also lower thermal expansion coefficient. To give you an idea, I'm gonna draw two curves, two potential wells, and then we're gonna compare it. Okay, so one of them can be like this, sharper. One of them is like this. Okay. Okay, so if we want to compare both these materials, this one, since the E naught is higher here compared to this one, so that means that this one has a higher melting temperature and high elastic modulus, but low thermal expansion coefficient. Think about it is related to the strength of bonding, right? If the bonding is so strong compared to this one, with heat it will not expand much to a larger extent. So the stronger the bonds are, lower the thermal expansion coefficient. Okay. All right. So we talked ceramics have covalent bonding like silicon carbide, and besides covalent bonding, ionic bonding commonly occurs in ceramics, such as in this case we are given some examples. One of them is magnesium oxide. And ionic bonding basically happening between the elements on opposite sides of the periodic table. Okay. So in covalent bonding, it is happening between atoms that have similar electronegativities, which are near one another in a periodic table. In this case, they share their electrons so that each atom can complete their outer electron shell and reach the noble gas electron configuration. And here the covalent bond is illustrated for hydrogen molecule. Hydrogen has one s electron. Okay, we have only one energy state and s orbital, and within it one electron. So to reach the helium configuration, it both has to have one more electron, and they have this by sharing their electrons. This way, in their outermost shell now have two electrons reaching the helium noble state, so stable state, right? And this is of course achieved by overlapping of the electron orbitals, the s orbitals of two atoms. The covalent bonds there, it's very strong, and therefore materials that are experiencing covalent bonding like ceramics and some metals, they have very high melting point. But this type of bonding, it is directional. So atoms has to come around each other at a certain orientation, at a certain angle to make the bonding. And why? Let's learn. So the answer lies in understanding bond hybridization, and it is the combining two or more orbitals. And this is often associated with carbon. So consider now electron configuration of carbon, right? It is 1s2, 2s2, 2p. So remember again, S and P just electron clouds, probability distributions in space where electrons can be located. So these are easily can overlap in space. And in some instances, this is what is happening. And because they overlap in space, electrons can move from S orbital to P orbital and making the configuration look like this. And now outermost orbital can, here you see one of them moving to the P orbital. And of course this will result in outermost orbital to produce actually 4 sp3 orbitals. So sp3 orbitals. 4 sp3 orbitals. And each of these have one electron in it. Okay, in total, because we have 4 and each of them will have 1, and in total you have 4 sp3 orbitals. This is going to result in directional bonding. The first thing is you can see there is an angle between, there's a certain angle in between the orbitals. Okay, and the other thing why it is directional, because think about 2 carbon coming together. This is especially important for polymers, okay? And polymer chains, carbon-carbon chains, how carbon is attached to another carbon, it is like a zigzag configuration. Because the carbons need to approach each other at a certain angle, at a certain orientation. The reason is now carbons need to share electrons, right? And the only way another carbon can come and share electron, it has to bring its sp3 orbital at a certain direction so that it can share electrons together with another sp3 orbital of another carbon. So they need to approach each other from a certain angle and from a certain direction. That gives this covalent bonding a directional characteristics. And of course this is an example of what we have just discussed. CH4 methane molecule which experiences sp3 hybridization, and we are seeing the carbon has 4 valence electrons, and in each one is in the sp3 orbital. And of course it's good if when hydrogen approaches, it has to approach at a certain angle, and their orbital, s orbital, will overlap with the sp3 orbital of the carbon, and electrons will be shared. Both atoms are reaching their noble gas configuration and filling of the outermost energy level with electrons. What about metallic bonding? Of course, this type of bonding found in metals, and it occurs between atoms with only a few electrons in their outer s and p orbitals. So valence electrons are given up by individual atoms, resulting in a geometric array of positive ions surrounded by a free electron cloud, as you can see. A simple model is shown. So the electrons are free to move in the structure. It is also called, they are forming a sea of electrons. Therefore, it is the reason why they can conduct electricity and heat and easily. And of course, the metallic bond, when we say metallic bond, it's basically this electrostatic attraction between these positive metal ions and these delocalized electrons. Okay. And many bonds are mixtures of 2 or more types of bonds. Okay, so metals can experience metallic and covalent bonding at the same time. One example is tungsten. And especially, you guys know, tungsten has a very high melting point. It is because of this presence of covalent bonding in the structure. Another most common mixed bonding type is covalent ionic bonding type. So there is an equation given to us, which is how we can calculate percent ionic character of a bond between certain elements, let's say A and B. And X represent the electronegativities. We just seen at the periodic table where the electronegativities of the elements were given to us. So X represents the electronegativities of A and B atoms. Okay. And we are given an example here. If we know the electronegativities, here we are given magnesium and oxygen. And we can easily calculate the ionic character percentage of that compound, magnesium oxide, to be just 73.3% by just plugging in the electronegativity values to the equation. Okay, secondary bonding. These are weak bondings. So very weak bonds can develop between atoms with filled electron shells because the atoms can attain a dipole character due to the asymmetry in the electron charge distribution. So these secondary bonds are van der Waals. Let me write it down. And hydrogen bonding. So what is dipole? Dipole means separation of charges in a molecule. So we know that electrons, they are constantly moving around, and at some point in time, temporarily, okay, one side of the molecule can be more negatively charged compared to the other side, because remember, if this is our orbital and electrons are going around, right, at some point in time the one side can filled with electrons like that, so making this side of the molecule more negatively charged compared to the other side. So such separation, of course, two dipoles, okay, charge separation. Of course, the negative side of that molecule will attract the positive side of another molecule because of electrostatic attraction. Okay. So dipoles in van der Waals, though you need to understand, have a fluctuating character. That means it is temporary, okay? It's not permanent. And this type of bonding actually can result in liquefaction, solidification of inert gases like hydrogen gas. And it is also important in polymers, because polymers are covalently bonded molecules, large molecules, but between the molecules there are weak forces like van der Waals. And therefore this is why they have low melting point, low strength, because normally polymers are made up of carbon-carbon bond, right? Carbon-carbon bond is a very strong bond, but what happens here, in between these chains, in between the carbon-carbon molecules, there will be, we're going to later learn in more detail, there will be weak forces like van der Waals forces. That is the main reasons why polymers have low melting point, although they have carbon-carbon strong bonding in their structure. And on the other hand, hydrogen bonding is stronger. It is not like temporary, it's permanent. Okay, it doesn't have this fluctuating character, it's permanent dipoles. One example is hydrogen chloride. Why it is permanent? Because chlorine is more electronegative than the hydrogen, pulling the electrons towards itself, making the chlorine side more negatively charged. So again, the positively charged side of this hydrochlorine molecule, one side positive, will attract the negatively side of another molecule. Again, the same electrostatic attraction in between them, causing this weak bond. But the hydrogen bonding is stronger than van der Waals bonding. Okay. We just discussed about this, and this is a summary of how the properties are related to the bonding. And one of them is melting point. Basically, the larger the bond energy E0, the higher the melting point, right? So this part is smaller here compared to this. So this one, this curve, the material represented with this curve, will have a larger melting temperature, larger melting point. Another property that is affected by the strength of the bonding is thermal expansion coefficient. In this case, smaller the bond energy, larger the thermal expansion coefficient. Again, because think about it, when a material expands, the bonds have to stretch, and if the bonds are weaker, like in the case of smaller bond energy, then they can easily stretch when the heat is applied, therefore causing a larger thermal expansion coefficient. And because this energy curve is asymmetric actually, when during the expansion the atomic separation distance increases. Because if it was symmetric, think about it, if it was like this, right? So average interatomic separation distance will always be R0. So it cannot change with the heat, the interatomic separation, but because it is asymmetric like this, okay, because it's asymmetric, this interatomic separation distance, the average of it is actually increasing. Okay. So this is pretty much a summary what we have learned. Ceramics can have ionic and covalent bonding, and this ceramics experience very large bonding energy that gives us high melting temperature, large elastic modulus, meaning stiffness, meaning the bond strength is very high. Okay, think about the bond is a spring in between the atoms, and it is very difficult to stretch that spring if you have a large E. And then that causes, of course, the small thermal expansion coefficient. And metals, they have moderate melting temperature, moderate stiffness, moderate thermal expansion coefficient. Whereas the polymers, as they are giving us here the carbon-carbon chain, in between there are weak forces, secondary bonding. Polymers experience covalent when in the carbon-carbon chain, and in between they have secondary weak bonding. It can be hydrogen and van der Waals. And this is because of that they have low melting temperature, low modulus. Think about rubber, right? You can easily stretch rubber. And large thermal expansion coefficient. So what we have learned that properties are directly determined by the electron configuration. Valence electrons very important because they are taking part in the formation of the bonds. And primary bonds are covalent, ionic, and metallic. Mostly these are interatomic. And in between the molecules we also have secondary bonds, van der Waals forces, or hydrogen, which are weaker. And we can calculate the percent ionic character of if there is a mixed bond between two elements based on their electronegativities. These are the things we have learned in this chapter.